Good afternoon, folks, and welcome to RST 1101 Introduction to MPLS. I hope everyone had good lunch and a good cappuccino or coffee or whatever you guys drink to keep you awake. If you feel like you're falling asleep and you just got to take a nap, raise your hand and ask me a question. Help you wake up. Help me wake up too, hopefully. All right, so we have a lot of material and we have, pretty breadth because MPLS, a lot of applications. Even if you look at, as a customer base, right, you have service providers, subscribers, and I imagine that I have a combination of a lot of different types of customers in here. Can you raise your hands to see who is actually planning on deploying MPLS in their network? Wow, a lot of you. Okay. Can you raise your hands if you're planning on getting an MPLS VPN services from an MPLS VPN service provider? Raise your hands, please. Okay, so we got good amount on both sides. And I have a lot of material, something for everybody. Sometimes some people are looking for in-depth material. Some people want just the breadth, and I have both of it. So hopefully we can get through all the material. I put in extra material for your reference. I will not be covering every slide. I've hidden some slides. So if you see, different slide here rather than what's printed in your printout, just jump to the, next couple pages and resynchronize with me because I've hidden some slides in here. But what I plan on doing is I plan on covering every key things that as a subscriber or as a provider that you need to know at a basic level as far as MPLS is concerned. So hopefully you'll enjoy the material. So what we have here is background of the technology. One thing we want to know, and this has been very popular technology. We've gotten great momentum. We have over 250 service providers worldwide deploying this technology and offering the services. And the next trend that we're seeing is a lot of our large to medium-sized enterprise customers are also rolling out MPLS in their network to support like segmentation type of services. So, one thing, whether you're a subscriber or a provider or you just out of curiosity, you happen to be in this class, want to know, what these buzzwords all about. We want to understand who are the players. Tell me what the protocols, what their role is, and what applications, are available, and how do I construct MPLS network. I want to offer layer 2 services or layer 3 services or just optimally, optimize my bandwidth usage in my network. How do I go by doing it? And so those are the things we are going to look at today. And once you learn the details about each of the protocols, then tell me how do I build this service? What type of services can I offer? Those type of things I'm going to be covering in this session. So with that said, my name is Sangeeta Pandya. I am from MPLS group in a division called NSSTG, stands for Non-Stop Serious Technology Group. It's actually Network Software Services Technology Group. And a lot of the features that go into Cisco IOS platform, get developed out of our group. So the next thing is, why did we come up with MPLS, right? And if you really look at the evolution in different network technologies like X25, that didn't meet some requirements, had some issues. We came up with frame relay. We needed more bandwidth. We wanted, better QoS functionality. We came up with ATM. And if you look at all these architectures, there's some, because we always want more, right? We want better, faster, bigger things to actually support the emerging applications. Those are coming up. So what we really needed is a single infrastructure that would support multitudes of applications, right, in a secure manner. We wanted an infrastructure or architecture that was very flexible, and, it allowed us to actually, converge our network faster if there was a network failure, help us make decisions based on our network capacity, or depending on the applications requiring certain resources, help me be able to, engineer my own net paths in my networks depending on what the applications are and what the requirements are. So this is the type of requirements we needed. So we came up with this architecture that supports several of the applications and, again, in a more scalable way than the technologies that we've seen. So as far as the customers are concerned, right, whether, what do they care about at the end of the day? Reduce my CAPEX, OPEX, and increase my ROI, right? Help me increase return on investment. Help me build more services so that I can offer more options and more services to my customers. So from the customer's perspective, what we were hearing is give us economical solutions. What does economical solution mean? So how to reduce your capital and operational costs? Well, one way you can do is you can collapse parallel networks into a single infrastructure. So if a service provider were to support 100 or thousands of customers or subscribers based on their unique requirements and to keep their traffic separate from other customers' traffic, they would have to build 100,000 parallel networks. Now you can imagine the cost that would go into building and managing or operating those type of networks. So again, being able to collapse parallel separate networks over single infrastructure, eliminating redundant and dedicated access links. Now if you look at ATM services, right, you had to support voice, you go ahead and get a PVC that will support CBR, which is a constant bit rate, because voice has a different bandwidth delay guarantees and requirements. And what we want to do is whether it's an internet traffic, voice traffic, video traffic, we want to be able to combine all these traffic over a single link that we're going to get or plug into the service provider's network. So again, being able to not just collapse the parallel networks, but being able to reduce on the access links that we need to connect to the networks. And other thing is, if I have a single infrastructure, I want to be able to consolidate my resources from the service provider's view so that I can offer virtualized services using the same resources. As far as the scalable segmentation solution is concerned, because whether you look at service providers, of course they're interested in keeping different customers' traffic separate. Enterprise customers, there's a trend that we are seeing. Initially they had VLAN-based networks, right? Pretty much wide open. The way you identified your users, authenticated, was all based on the VLAN. They belong to certain VLANs. Then the next trend that you saw is people moving away from VLAN, just having it at the access layer, because spanning tree algorithm loops, a lot of broadcasts on the networks, etc. Right? So you went ahead and said, okay, layer 3, I'm going to move to layer 3 for my core of the network, and my edge of the network, enterprise network, can use VLAN, and that's how I'm going to keep traffic separate. But there's more and more requirements, security requirements, and for more and more critical applications, and enterprise customer subscribers are requiring that a lot of their group-based or departmental-based or application-based traffic that they want to segment and separate the moment that from it enters the networks all the way to its destination. So VPNs by organizations, sub-organizations, or departments, and if I'm going to have all these VPNs, I want scalable solutions, right? I don't want to have to touch at every part of the network if I want to add a VPN or if I want to remove a VPN. So anytime you want to add a service or remove a service, you shouldn't have to make changes everywhere in your network. So that's another thing that our customers are looking for, simplicity of provisioning and deploying the network. Bandwidth management, no network has just, equal paths, right? OC48 everywhere from end to end in the network. You're going to have combinations of GIGs and fast Ethernets and OC48 and DS3s or DS1s, channelized T1s, whatnot. So we want to be able to understand overall, what resources do I have available in my network, and how do I efficiently utilize it so that I can minimize the packet drop, I can minimize the delay in the network. And of course, simplified networking, because I have hundreds and thousands of sites. I don't want to have to, go to each CPs and worry about fully matching every site, because that is not a very scalable way of doing things. So again, to address that, that's a customer issue, and that's what we wanted to address. And moving beyond connectivity, it's fine, we got a secure connectivity, basic connectivity that's scalable and easily deployable, but I want to be able to offer and add more sophisticated services on top of this type of infrastructure. So those are the requirements, and let's see how MPLS will look at each applications that actually meets these requirements, and those are both coming from the service providers as well as the subscribers. So what does MPLS stand for? Multi-Protocol Label Switching Technology. And what does it mean by label switching technology? That means anytime we want to forward the traffic, we're going to look at the label values to make that decision. If you want to take the traffic or packets from point A to point B within a network, we no longer look at the IP headers, because in the routing, right, in IP networks, how do we forward packets? We look at IP header and we look at the destination. We have our routing protocols that has figured out, calculated the best paths, and we're going to look at what's my next hop and what's my egress interface on this particular device, and that's how I'm going to make a forwarding decision. Well, we're going to look at completely different value to make that forwarding decision when we use MPLS. And that's the whole, trick is in the MPLS networks versus compared to IP networks. If you look at ATM networks, right, you rely on your PVCs, VPI, VCI values to actually move the traffic forward. DLCI is in your frame relay, right? So same thing in MPLS. Again, we introduced a new entity that's actually going to help us make decisions on how to actually build our control planes and then build our forwarding planes and actually forward the traffic based on this new value or something called label that we're introducing. And when we have this new technology, we want it to be operable with existing stuff that we have, encapsulations, for example, ATM, frame relay, PPP, HDLC. We don't want to, completely get rid of those things as well. So, how do we make it work with all these other encapsulations and the networks that I'm used to having, because no customer is going to rip off, their ATM network in a day and replace it with MPLS, right? So we have, we want a good migration strategy as well. And just to sort of move to evolution, what have we done in the last 9 to 10 years? What have we developed? And I know all the way back in the row you cannot see what I've got on the board, but this is just a list of some of the features that we've developed over the past 9, 10 years in, different areas of MPLS. And if you can't see it, that's fine. This is a hidden slide that I have, so you guys don't have this in your printout. There are a couple other slides that I've added more information to, and if you want the latest version, give it a week and log on to the Networker site, and you can download the latest presentation. Okay, so you won't miss out. And these are just the features. You can log on to Cisco.com, look at the feature navigator for, the platforms of interest, and it will also give you the list of some of these features as well. So no big deal, just trying to make a point. If you look at when the whole thing began, when the whole evolution began in 1996. We're in 2006. Epsilon actually was thinking about coming up with a circuit cross-connect type of technology and do sort of flow-based switching, because they wanted to, move away from this routing, which is having to do longer IP address matching, right? And so they were looking at a new technology. Well, flow-based switching or cross-circuit connect technology wasn't very scalable. So there were some Cisco fellows also at IETF. They came back and, thought about a few more things about the technology and developed a text switching distribution protocol, which is what we call TDP. And TDP was the first guy, new kid on the block, that was enhanced further and changed the name to LDP, Label Distribution Protocol, that we'll be talking about a little later. And after that, additional applications were developed. So as the tag switching took off, because the customers wanted to isolate their core, service providers wanted to isolate their core, and to make the control plane, forwarding plane faster, just deploy the switching technology. And don't care if I have layer 2, layer 3 VPN services for my subscribers just yet, but let me have a single infrastructure and separate my core traffic from my edge or my customer traffic so I can protect my core better. Okay, so that was the thoughts behind the initial deployment. Then additional applications came in later on, layer 2, layer 3 VPNs, and now if you look at what we're looking at is we have very large networks deployed with thousands of VPNs and whatnot. So, of course, high availability is very much a concern. Faster convergence is very much a concern. And, security, how do I make my networks more secure? And adding additional services, like take some traditional IP services and make it MPLS aware so that they can function very similar way without me having to lose any functionality in the MPLS environment. So if you look at the network infrastructure, initially I mentioned, hey, we want a new infrastructure, but the new infrastructure we want needs to be very flexible. Be able to work with the current existing technologies or the architectures that we have. So if you take at the network infrastructure level, you can take any frame relay or ATM network and deploy MPLS on top of that. And how do we do that? If you have MGX 8800 switches, for example, add a label switching router blade just on the box. So it just takes a upgrading to one hardware blade, and that speaks MPLS, understands IP, and is an easier migration path to IP networks. And that's what we saw initially, because a lot of service providers had ATM networks, and I think even as a subscribers, I'm sure you're noticing that frame relay ATM service services are becoming more and more legacy type of services, and you're being able to buy MPLS VPN with more bandwidth, but cheaper connectivity services and even more secure services. So again, going back to the infrastructure level, that's what the service providers initially, started deploying IP plus ATM solution. Then we came up with provider provision VPNs, the first box right here, layer 3 multi-point VPNs, and now we're coming out with layer 2 multi-point VPNs as well. Traffic engineering, we'll talk about each one of these applications a little later, but again, how do I efficiently manage my bandwidth, utilize my bandwidth in the network? And this was probably the second guy. Right after the layer 3 VPNs, traffic engineering was introduced. After that, any transport over MPLS, that's layer 2 VPNs. You have PPP encapsulation, or you have ATM islands that, you don't want to migrate to IP, or you don't want to migrate to MPLS, but all you're looking for is getting MPLS connectivity or a transport across the WAN wide area network from your service provider to interconnect these two ATM islands. That's all I want. I don't want to upgrade any devices or upgrade my protocols and convert my ATM to IP. So that type of migration is what any transport over MPLS facilitates. GMPLS, IP plus optical, GMPLS optical-based solution. Again, I'm going to build my label switching paths based on my wavelengths, etc. So if I have SONET SDH or any additional type of networks that my traffic is going to cross, like frame relay, ATM, SONET, right? It shouldn't experience the difference. The packet shouldn't know and have to, conform to frame rules when it's going to the frame relay network. It shouldn't have to conform to ATM now. The next network is. It shouldn't have to conform to ATM rules when it's going to the ATM network. So actually coming up with a unified control plane and forwarding plane that will facilitate the traffic end to end regardless of what medium it's crossing. Okay, so that's GMPLS, generalized MPLS. So I talked about higher level what applications we have and what were the customer's requirement and how, why we came up with these applications that we did and why we're seeing, such a great level of adoption of this technology in the industry. So let's take a look at what are the key players. If I wanted to build my MPLS network, what components am I looking at? Or as a subscribers, of course, you're handing your traffic to MPLS providers, right? You want to know what's going on in their network and how your traffic is handled so that you can gain confidence and faith in the service provider services and this technology. So IGP is a core routing protocol that the service providers runs in their core that is completely separate from the routing protocol and the routing updates, etc., that goes on in the VPN sites of their subscribers. Okay, so they isolate the core, they run their own IGP, OSPF, EIGRP. You can even do static routes, so there's no limitation on which routing protocol you have to deploy in your MPLS core. If you were to deploy traffic engineering, is one of the applications you feel you need, then of course you need OSPF or ISIS, and I will tell you later on why that is. But next thing is, of course, label, because that's the one. That's a key player that we're going to make decisions based on, right, to forward our traffic. Encapsulations, I have ATM frame relay. I'm doing maybe frame mode ATM, cell mode. How do I, where does the label go within this frame? Forwarding equivalence class, what is that? FEC. Forwarding equivalence class changes depending on whether you're looking at layer 2 or layer 3. Layer 3 could be your IP, all your IP prefixes. Okay, so forwarding equivalence class is the one that is going to work with the labels, and that's the type of traffic that we are interested in providing the transport to. Label distribution protocol, additional MPBGP and RSVP, all three protocols are actually used to, get labels, generate labels, and hand off labels to their peers where the labels are needed for each of the prefixes. So label generation, distribution, label binding to your fax or prefixes is all, that's all handled by this label distribution protocol. Let's take a look at generic service provider MPLS network. Okay, what we're looking at is MPLS core that is all enclosed within this cloud. Here a couple different terminology. LSR stands for label switching routers. P stands for provider router. and that's a provider core router. Because there's a PE, there's also a provider router, but it's a provider edge router. The reason why we have different terminology for P routers and PE routers is because they have the different roles. Certain services that you're going to switch on is only going to be on the PE devices, only at the edge. So later on, we'll see that only the edge has a knowledge of the remote sites. And the core is only interested in whatever that PE hands off. It's only interested in switching the packets from ingress PE to egress PE. And that's how we made the architecture scalable, because notice, PEs have different knowledge, right? Different information. P has different knowledge, different information. Not everybody has to know everything about everybody that goes on and every services that goes on out there. So with label, what do we do with label? Label imposition, label swapping, and label disposition. Those are the three functions that we do with labels. When do we apply labels? Now, MPLS is only in the MPLS service provider core. Now, there's some enterprise customers or subscribers might be also deploying MPLS in their network, right? So then that's their network or their core that has MPLS knowledge available. But anyways, it's inside the core that MPLS is relevant. If for services, the remote sites, getting MPLS VPN services, whether layer 2 or layer 3, whatever the technology you're using here, that's the interface that is going to see on the provider side. Okay, so between the remote site and your PE, it's only IP connectivity if you have the layer 3 VPN connectivity. So your subscribers' networks, they don't care whether you're connecting to the MPLS network or whether you're connecting to the IP network. So as far as CPE edge device that the subscriber is concerned, it's very transparent to what the service provider has deployed in their network. So label imposition, packet comes in, we apply the label, we swap the labels in the middle, and why we do that, I'll show you in the next couple slides. And of course, we want to pop the label. We want to remove that label because we want to hand that packet as IP packet. If you hand the packet with the label, the remote site customer's CPE router is not going to understand, right, what this is. So we don't want that situation. So we want to hand the packet off as an IP packet. If it was an ATM network, we want to hand the ATM cell back to the remote device. So if you're talking about label switching and swapping and appending the labels onto the packets, what does my label header looks like, right? Because every header looks different. IP header, right? PPP header. Every header's got some values that has some meaning to it. So this is a 4-byte header, and in that header we have few values that we are going to look at to make decisions. Label itself, the value that we use itself is a 20 bits or 2.5 bytes. And experimental bit value, that is again for traffic prioritization. In IP header, what do we use for traffic prioritization? Marking packets, classifying packets, we use type of service field, right? And in the experimental bits are used 3 bits again in the MPLS network. So we have 8 classes, 3 bits, 8 levels, 8 priority levels, or 8 classes that you can create within the MPLS network. And TTL, time to live, for detection, etc., that again we have here, and pretty much the same format. In the MPLS network, what happens is the IP packet comes in, we take the TTL value from the IP packet, and we put it on. We copy it into the MPLS packet, or this TTL field. So that's what the label looks like, and those are the values we refer to and to make different decisions. So before I move on to the next slides, is everyone understanding this pretty well so far? Is the pace pretty good, or am I going too fast and you want me to slow down? Pretty good. Okay, good. Thank you. So next thing we want to look at is I have a label. I know I'm going to be swapping and appending and removing it at some points in the network, but where does it go exactly in the packet if I have different encapsulations? PPP header, again, goes between the PPP and the layer 3, so between layer 2 and layer 3. I think the easiest way to remember this is consider MPLS as a layer 2.5 technology. So between the layer 2 and layer 3, we go ahead and insert the MPLS or header. In case of ATM MPLS cell mode or LC ATM, the label controller one, remember the first application that I mentioned where you're using the MGX ATM frame relay switches and you put the label switching router blade? In that mode, we actually map our label right on the VPI VCI. So if you look at any of this encapsulation and you look at the label value, you'll have a single value. It will say 10 or 20 or 30 depending on whatever it's figured out. Here, it will be 101/2 200, for example. Whatever your VPI, VCI values are, that is what your label is. So follows the same format. I mentioned forwarding equivalence class. Hence, could be IP prefix or host address. And this forwarding class is the class or the values that we're actually going to allocate the labels for and map the labels to. So if your FAQ is IP, and you're dealing with layer 3, then you look at IP prefix 10.10.10.0. Tell me what the label is for it. 10, for example, or 20, for example, and I do label mapping. So that is the forwarding equivalence class. Layer 2 circuits will have, different values, VPI, VCI, or frame relay that I'm going to be creating labels and mapping to. So forwarding equivalence class is the traffic that you actually want to forward in the network, and you want to bind your labels to, so that now you can look at your labels to forward the packets. So a couple key points. Who's going to be doing all this work, right? If we need the labels and we got to bind the right labels to the right prefixes. Yes. Okay, so what is the FAQ in a layer 2 when, for example, when you're using PPP header? If you notice, PPP header has point-to-point protocol, right? When you have two peers, it goes through like 3 different layers. The link layer, negotiates the link layer, etc. And of course, it gets to the third layer, which is the network layer, where it actually gets the IP address. So it's going to have a PPP header with the PPP values, the timers, all these other things that it wants to look at and make decisions and understand that, like a version number or the packet type that the router looks at and says, hey, okay, I understand this is a PPP packet, okay? So that's a label type that it looks at. So again, when you negotiate the third layer or the network layer in your PPP protocol, at that point, you have 2 labels or 2 headers with your PPP encapsulation. Like you enable HDLC encapsulation between your 2 routers. You can also enable PPP encapsulation. And why do people use PPP encapsulation? Is because they want to do authentication. Okay, and you can do authentication in, you have a couple different options of authentication. I won't go in the details, but again, the thing is, you'll have a PPP header as well as you have an IP header with your PPP information. In any case, and again, same thing with the PPP, right? As the packet gets forwarded, whoever the entity looks at the PPP header to make that decision, will look at the PPP header. When it gets to the layer 3 in the routing domain, it's going to look at the IP header to make the decision, where do I forward the packet. So again, you got those 2 labels, and that's right in between you want to insert the label. So in the MPLS network, we will no longer look at the PPP header or IP header to make the decision. So if you're in the dial networks, PPP is used very much, right? So ISDN, you're doing a dial-up network, PPP is negotiated. Only that interface that it's dialing into on the PE router is going to care for the PPP header. After that, if you turn on MPLS on that dialer interface, it's going to look at the labels. Okay, that's what it means. So going back to the label distribution protocol, a couple key things we want to look at, because this is the guy. This is the guy in charge of getting you the labels and advertising the labels and helping you bind the labels and get them across, every hop or every LSRs that you have in your network. You may have 2, or you may have minimum you need is 2, and maximum is you decide. So what does the LDP header look like, right? Like I mentioned, every protocol has a header. So version numbers, PDU length, and one key thing is LDP ID, and has 6 octets. So 4 octets are used for the router ID, and I will tell you a little later why LDP header carries the router ID. ID of that LSR, maybe it be a loopback address, and that's the recommendation, right? That's the best practices. You want to use loopback addresses. So that's the address it's going to carry. What happens with the next 2 octets, because that's only 4, the next 2 octets are actually used to indicate where the labels are coming from, because you have 2 types of label space where you can actually pull out labels from. You have interface label space that's used in ATM, cell mode environment, and you have with packet mode, frame mode. For the rest, for the most part, I think the most applications or most deployments that you're going to see uses the global space, and that's what this guy indicates. And this is what sent to its peer. Its peer, when it sends the hello packet to its peer, it's going to have this value. So the peer looks at it and says, I'm getting a hello message from 192.20.20.1, and it's going to use global space, because the 2 has to agree on which space they're going to be pulling the labels out from, okay? And then there are additional things that go on, additional phases, additional modes to do, allocate labels and stuff. And I promise you, this is the headache you only go through this one time for the next few slides. Deployment-wise, it's made very, very simple. 2 commands, and all these operations that we are talking about, it will take care of all these operations. So building and provisioning of MPLS network is not going to give you this much headache as you're going through the first few slides, because I understand there's a lot of information, just this particular protocol. If you don't get everything, that's fine. Just understand that if you want to turn on MPLS, the 2 peers, just like in any protocol, is going to be, discovering each other and going to be exchanging some values, and they're going to have to agree upon some values, and that's when the sessions are going to come up, and there will be maintenance messages and tear down messages, etc. If you just get that much, that's pretty good to take home. And so discovery mechanism, again, 2 different types of modes: basic discovery, neighbor discovery, and extended neighbor discovery. Basic discovery happens between the 2 LSRs, 2 label switching routers. Those are connected point to point, directly connected. Okay, that's for some applications. Extended neighbor discovery, we also call it LDP, targeted hellos or targeted LDP sessions. We'll see that it's actually used in the layer 2 VPN environment. And in that case, your neighbor could be sitting 2 hops away or 10 hops away. It doesn't matter. It will figure it out. And the hello messages are broad, multicast messages use UDP port 646. Rest of the sessions and everything is done based on the TCP. And this is why I mentioned the router ID earlier, that it's very important in the LDP header, because when you turn on MPLS, enable MPLS on the 2 neighbors, they're both going to send TCP message, right? Or they're both going to send the session initialization message. That's a TCP type of message. So what we don't want to do is we don't want to establish 2 TCP sessions between the 2 neighbors, okay? So whichever neighbor has a higher router ID, that's the one that's going to be in control to actually create and maintain the LDP session. So that's the guy that's going to say, hey, hello, yeah, I know you're out there. Here are the values. The next guy is going to say, okay, I agree with those or I don't agree with those. And then this guy is going to acknowledge all that stuff. So question there. Okay, when I say LSRs, do I mean PE routers or P routers? When I say LSRs, I mean PE and P routers. Because although we said we don't enable LDP or we don't enable MPLS on the customer-facing interfaces, on the PE routers, we do have to enable that on the core-facing interfaces. Okay, so the PE routers will have MPLS enabled on the core-facing interfaces. So they're essentially also label switching LSRs or, label switching routers. But PE and PEs is more commonly used terminology in the field. Good question. So again, what's a negotiated label distribution method? Timer values, when the LDP session is going to expire, if I don't hear from you 3 times or 4 times, what are my hold down values? Very, pretty similar to the routing protocols that you've seen over the years. Label ranges, because we have 20 bits, so 2 to the 20, we can have over 1 million labels. First 16s are reserved for some usage, and then thereon you can use any. You can statically define the label range that you're interested in, or let the LSRs do their own thinking and allocating. Okay, so that's a little bit more on the label range there. So once we have that session is established, the next thing we want to do is label binding. What does it mean by label binding? That's label mapping between the FEC, right, and the labels that we produce. That means 10.10.10.0, I want 20. And so when the packet comes in for 10.10.0 network, I'm going to use label 20 to forward that particular packet. And that's label binding. And how do LSRs get labels, right? There's a downstream unsolicited and downstream on-demand mode. A couple different ways the labels are handed out to the neighbors. And why does the neighbor hand out label to its neighbor? Because the neighbor can also calculate its own label because the routing protocol is already synchronized. Remember I said the first thing you want to do is IGP. So all the routers know all the destinations, right? And they're all capable of calculating labels. But the way we follow it is there's downstream unsolicited mode and downstream on demand. Unsolicited mode that says, and the downstream router is the router that is sitting the closest in the MPLS VPN net or the provider network, that is sitting closest to the destination address. That is the downstream. So it will say, oh, I know, it tells its neighbor, I know how you can reach here, and I want you to use label 40 to go over there. Okay, that's downstream unsolicited because this guy has told this guy what to use, what value to use without this guy asking it. Downstream on demand, this guy asks, I have this, I know this prefix, which label do you want me to use, for example. Couple more slides and things will, I promise you, things will get more interesting. Independent mode and order mode. Independent mode is the independently it knows the routes. It's going to calculate the labels. It's not going to wait for its neighbors to assign it. Ordered modes are it waits for its neighbors to actually provide the bindings. Downstream unsolicited mode has two type of label retention because we created labels, we map labels. How long do we keep these labels? If the route goes down, link goes down, etc., right? So label retention mode, liberal one, is the one that it keeps all the labels regardless whether this LSR or this particular prefix is right next to it or next hop, and whether it's going to use it right away or not. Conservative label retention, it only keeps the labels that it knows it's going to use right away. And one helps you, save some space on your router, save some memory on your router. And another one helps you actually converge your router faster if the link goes down. So if you have multiple paths, this route goes down, I can pretty fast forward my packets in the other route because I already have the information available. Okay, so now all of that details passed. Let's go back to the MPLS network and let me re-summarize some of the things that I mentioned. First thing you do is you enable IGP. Could be OSPF, ISIS, EIGRP, static routes within your MPLS core. The core-facing interfaces are these particular interfaces. When I say core-facing interface on your PE router. Enable MPLS on the core-facing interfaces here as well as there, and all the interfaces in the middle. And all the theory that I talked about, right? And if you look at the RFC, is over like 130, 150 pages. It all boils down to these 2-3 commands that I have here. IPsef, at the global level, this is the configuration example that we're looking at on page 24, is IPsef. Of course, you need to enable Ceph because all the tables are Ceph switched. One command that you need at global level is MPLS label protocol LDP. Why you can choose between TDP, the old one, or you can have LDP. Most of the networks now have already migrated to LDP. So you specify what you want to use. And on the interface that you're interested on turning on, enabling MPLS, you just say MPLS IP. Very short command. Perhaps probably the shortest command I think that you will come across. And that's all it takes. And your core will figure out labels that it needs, etc. And later on, you can just sit back and look at your forwarding tables and look at what it came up with. What labels did it come up with for what prefixes? Okay, and it's not necessary that you enable MPLS on every interface, but if, end-to-end, look at the paths and make sure that you have, for efficiency, you have MPLS IP enabled. You could have a couple more routers out here in the core that was just purely IP path, and that's completely all right. We're going to look at downstream unsolicited mode because, we want to look at how the labels are handed and the mappings happen over here so that you have clear ideas of what to look for when you're actually looking in, troubleshoot or verify your networks. Yes?
So it's not an all or nothing thing?
Yeah. It's not all or nothing thing, implementing MPLS. For example, you have IP network and, you want to migrate to MPLS. How do I do it? You don't have to tear down the whole thing or you don't have to build the entire thing. You can start with 3 routers and build it in parallel. One router, which would be your core router, and 2 routers PE routers. That is if you want to offer the layer 3 or layer 2 VPN connectivity. And you can have IP network right there in parallel to the MPLS network, because then at the edge is where you can decide which traffic you want to put over which path. And just because you have 3 routers doesn't mean you just put the links, connect only those 3 routers, and then, as you pick maybe one more router that you want to make it MPLS, add more links, enable MPLS on the link on this side, ingress side, and the link on the egress side, so that the full path is now MPLS. But this router may also have other IP links that it's supporting IP. Okay, that's how you slowly move from your IP networks to MPLS networks. Unless you're very rich and you got the budget, we got a lot of routers to sell. So you're welcome to build the full network, full-blown network in parallel to what you got today. IP packet forwarding, this is just an example. You guys been looking at this for ages, right? So it's your IGP populates IP routes and the packets are forwarded. No big deal. Now I enabled MPLS. Notice the difference on slide number 27. What happens is I got 2 more columns, okay? In label and out label. So let's see how those in label and out labels are actually utilized. So right here is the prefix, right? 128.89, 177.69. And these are the prefixes or the routes that we are going to be learning. These networks learned already, and that's why your IP routes column is actually filled already. The egress interfaces, it's figured out already. Now let's see how I figure out the labels for this packet, for if the packet comes here for 128.89, how the labels are calculated so that it can be forwarded to the other side. So this guy says, this is a downstream guy, it tells its neighbor, hey, I know where this destination is, and I'd like you to use label 9 anytime you want me to forward packets to this guy right here. Same thing, 171.69 says, anytime you want to forward me the packet, use label 7. Okay, so what this guy does, it listens to its neighbors, and it takes the label 9 and it puts it in the out label table or outgoing column, and it puts 7 for this prefix in the next entry, and it maintains that. Now this guy says, I know where the 128.89 and the other prefix is, but I'm going to tell my neighbor what label to use. And this is, notice, what's really making the architecture very secure, because this is the LSR that says, hey, use this label. If it doesn't use that label for that prefix, it's going to discard the packet. So if you have VPN sites and people are trying to spoof label and send traffic with the wrong label, guess what the interface is going to do? It's going to drop that packet. And even though the packets are coming in from, let's say, they've spoofed the right labels and they actually label the traffic and it's coming from the remote site with the correct label, on the interface, the router knows that MPLS is not enabled, and I don't expect that remote site to be sending me any packets with labels, so I'm going to discard it. Okay, so at the infrastructure level, the whole solution is made very, very secure. So this guy says, okay, my neighbor's telling me to use label 4 for this prefix and label 5 for that prefix, and that's exactly what I will do if I want to send packets to those guys. Notice this column in label, why is it empty? Anybody can tell me why that column is empty? Absolutely. Because the next guy is not using MPLS. Whether it's within the service provider network or it's the remote customer site, MPLS is not enabled. So that's how this guy knows that, hey, my in-label column is empty, so I expect IP packets to be coming in. And when they come in, that's at the ingress point is the only point it's going to do IP header lookup, destination lookup, or the longest match. Thereon, it will append the label and make decisions based upon those labels. And this is your forwarding plane. We looked at the control plane, the signaling how the labels are established. Now when the packet actually arrives, 128.89.25.4, this guy says, okay, I am going to look at my RIP table, and I know my egress interface, and I know what the label value my neighbor wants. That's exactly what I'm going to append. So when this guy gets the packet, it no longer doesn't know what's in here. Layer 2, layer 3, encrypted packet, doesn't care. Doesn't look at it. It only looks at the outer label. The outermost label is the IGP label. That's the term we use, IGP label, for the core core switching. So it looks at 4 and says, okay, I know what I need to swap 4 with, 9, because my downstream neighbor wants me to use label 9. So it's going to put label 9. So when this guy gets it, it says, I have label 9. It looks at, says, oh, in my out label, I have null. I don't have any labels. So that means I need to look at the IP prefix. And it looks at the IP prefix and it knows what the egress interface is, and bang, it removes this packet, the label, and it sends the packet out as IP packet. Okay, that's how the things are taken care of in forwarding paths. So you see in the MPLS, and this is handed down to all the applications from the basic architecture, is control plane separate from the forwarding plane. Control plane does the signaling, establishes the LSPs or label switch paths, which the forwarding plane uses to forward the packets. Couple more protocols, RSVP, resource reservation protocol. Some of you using voice over IP application might be used to using that for call admission control, but that's not what we're going to really focus on in this session. We're going to focus on it. It is used with traffic engineering application to actually come up with labels. See how label distribution protocol, LDP, came up with the labels? RSVP is capable of doing the same thing. BGP is capable of doing the same thing, except for they're used for different applications. When we use layer 3 VPN, we'll use BGP or something that we call multi-protocol BGP, which is the enhanced version. And this is a sort of re-summarizing and reinforcing that you got separate control planes and forwarding planes, and who are the guys in control plane in charge. BGP, LDP, RSVP, and your routing protocol, OSPF, EIGRP, whatever that is, who are the guys in charge of your forwarding planes are the labels that's calculated, and your CEF tables and your label forwarding tables or your FIP tables, forwarding information base, okay? And that's what this sort of gives you an idea, a pictorial view of routing adjacency is established, routes are populated, RIP tables, routing information base is populated, MPLS interacts with it, binds the labels, maps the labels to the prefixes, and what gets populated at that point is lib. Label information base is a huge table, and not necessarily that your forwarding table will take all these entries and put in it. Okay, so your CEF table may not be as large as your lib table, or your LFIP table may not be as large as your lib table. So next thing the RIP does for IP, it puts it in this is a finally derived routing table, FIP table for IP traffic. And for MPLS traffic, it hands off to the MFI, MPLS forwarding infrastructure. And that's where your LFIB and your lib and all these guys are sitting. It's a pretty efficient infrastructure. So if the traffic is coming in that needs to go from IP to MPLS, we look at FIB table. If the traffic is coming in and needs to go from MPLS to MPLS, we look at LFIB table. If the traffic is coming and needs to go for MPLS to IP, we still look at LFIB. So what's the trick to remembering that is if it's got label, the table you're going to use better have L, right? That's the only difference, okay? And if you're using multiple applications, because some MPLS networks could have just layer 3 VPNs, some could have layer 2 VPNs and traffic engineering, QoS, etc. Depending on the numbers of applications, we're going to do label stacks. So remember for your PPP, you had PPP header and the layer 3, and we inserted this IGP label right here in the middle. Now you're using TE application. We add another label, and that's going to be the outer label. Your IGP label will be like right behind it. If you have VPN, if you're using VPN application, it will still go right in the middle. So now you're looking at, maybe 3 MPLS labels for 3 different applications, or 2 MPLS labels for 2 different applications. If you only have VPN, then you're going to look at the VPN label, which is the inner label, and the IGP label, which is the outer label, and that's the label it's going to look at the core to switch the packet from PE1 to PE the PE2, ingress PE to egress PE, it's going to look at the IGP or the outer label. And the VPN application is in charge of sending the packets to the right VPN site. It's going to look at the VPN label, so that will be the inner label. And then we'll go a lot more in detail when we talk about the layer 2 and layer 3 VPNs. Okay, but what we're done with right now is core part of the MPLS network. Whether it's enterprise owned and operated or whether it's service provider owned and operated, what we talked about is MPLS core, what happens on the P devices, what happens on the PE devices, as far as establishing the label switch path within your MPLS network. So next thing we're going to look at is application, virtual private networks. What is a VPN, right? VPN is, any kind of a group that has different or unique policies or the rules. And these rules apply to the users of this particular VPN. And the two VPNs can overlap, and the users within two different VPNs should be able to talk to each VPN. So you can have one VPN in your single enterprise, or in your entire company, you could have multiple VPNs in a single organization. So, the VPN model, again, is very flexible. So tell me what's the difference between MPLS layer 2 VPNs and MPLS layer 3 VPNs, right? Because I need to make a decision. I'm an MPLS VPN subscriber. Which one's better for me? Which one do I go with, right? Or I'm an MPLS VPN service provider. Which service should I build first? Because, what are subscribers interested in most, right? So that's what we're going to look at. Well, MPLS layer 2 VPNs just provides you with point-to-point connectivity between any two sites. So if you're looking at multi-point connectivity between your 3 sites or 4 sites or 100 sites, you got to look at layer 3 VPNs. The only thing with layer 3 VPNs is the subscriber's site, CPE router, actually exchanges the routing information with the provider edge router, the PE router, the router sitting at the edge of the service provider. That's the difference. With layer 2 VPNs, Atom, point-to-point connectivity, you don't have to do that. It will take whatever the encapsulation you're using takes ATM, and whatever you feed through that particular pseudo-wire, particular tunnel, it just provides the transport over that wide area connectivity. So that is the difference. And depending on, whether you're very sensitive to actually exposing your routing information to the service provider or not, you can make decisions based on which solution you want to go with. But notice that if you want full mesh connectivity, then your service provider is going to have to fully mesh all these sites manually using the layer 2 VPNs. So with layer 3 VPNs, you compare it with what was wrong with GRE tunnels and IPsec. I've been using that and fully mashing my sites, right? What is MPLS layer 3 VPNs offering me? Well, if you look at those GRE tunnels, IPsec tunnels, etc., or going over, doing layer 3 or frame relay ATM type of networks, it's a connection-oriented type of connectivity. Every site that needs to be fully mashed, you got to have, go to every CPE device and fully mash it and maintain those numbers of routing peers, etc. Here you have a connection-less model where you have a point-to-cloud connectivity. And, service providers can offer virtualized services like I mentioned before. Here, services actually have to be sitting within the VPN customer sites. Other thing is overlapping private IP address space. With GRE tunnels or IPsec or any other, layer 3, that technology that you're used to using, you're going over the internet. Guess what? You have to do either address translations or use public addresses, right? Anytime you are entering a public domain or you want to communicate with another VPN site that's using the same address space, it's mandatory for you to do address translation. Here, for VPN sites to VPN site connectivity, your two departments, even in your company, are using overlapping private IP address space. Well, dedicate a VPN to each one, and they will be separated, and those are supported. So let's take a look at how the traffic is kept separate, right? How the overlapping address space with the same private IP addresses is managed. Because what did we learn so far? We learned that the core is pretty well secure, right? What we want to learn now is that the edge is secure as well, and that the way the customer's traffic is handled is also pretty secure. Okay, so in both control plane and forwarding plane, what we're looking for is good separation and good segmentation. So what you're looking at is a MPLS VPN network. You can, for now, forget about these P1 and P2 devices. Okay, let's focus on PE1 and PE2, because anything you're provisioning here, routing information, VPN information, these guys, like I mentioned earlier, don't care. Very transparent to them. They're blind to anything that's going outside over here. They don't care. Give them a packet and they will switch it to the egress destination point in that cloud. So forget about right now, just focus on what happens on PE1 and PE3. We got two VPNs, blue and yellow. CE1 and CE2 part of one VPN, CE4 and CE3 part of another VPN. So what we do is CE to PE connectivity again is IP connectivity. If this subscriber here is using OSPF, EIGRP, technically speaking, Cisco iOS supports all routing protocols for CE to PE, including a static route. What you will be able to do will depend on your service provider, what protocol, CE to PE protocol, your MPLS VPN service provider supports. If they only support static routes, you're going to have to convert to static routes between the CE and PE. If they support only eBGP, which is in a lot of the cases they only support eBGP and static routes, then if you're using OSPF, EIGRP, whatever your IGP is, you're going to have to redistribute it into eBGP. And that's just the plain eBGP that you're used to hand the routes out to the PE1. Now, PE1 runs additional protocol to IGP, right? Because it's got to run IGP to include this core-facing interface like OSPF or EIGRP, whatever. But on top of that, to provide this VPN connectivity, it doesn't use IGP. It uses something called MPBGP. Multi-protocol BGP is an enhanced version of BGP. We added additional communities to carry the VPN v4 information, okay, so that in the control plane, when the route comes from VPN A to VPN B, we append unique IDs or unique labels to keep these routes separate. Okay, that's how we keep things separate in the control plane. So with BGP, what is the rule with IBGP is that all IBGP peers have to be fully matched, right? If I had more PEs here, as far as the BGP sessions are concerned, between these PE devices, they got to be fully matched. But this is eBGP, so this eBGP doesn't have to be fully matched with this guy, that guy, other PE routers. Okay, so that's separate. Unless you're doing dual homing, for your backups. You got multiple CEs going to multiple PEs, that's fine. You need to load balance, that's fine. But on the basic terms, this guy peer up MPIBGP with this one. In addition to the regular IBGP information that we enter, like the BGP neighbor address, AS number, you also add additional VPN v4 address family, something called address family VPN v4, and you again say, support this functionality. You indicate that in the configuration. And they exchange and you have the sessions established. Once the sessions are established, then it's time for this PE router, because remember the CPE already redistributed, give all the routes to the PE1, associated those routes to that particular VPN. It redistributed eBGP into the MPI-BGP, right? That PE1 takes all those routes, attaches additional attributes or communities that corresponds with the particular VPN, and then it takes a whole bunch of those routing updates and gives it to the egress PE. So notice I have RD, next hop, it marks itself as a PE1. PE1 is also calculates the label. Why? Because this destination is sitting closest to it, right? So it's going to calculate the label and tell PE1 that, hey, you want to send me a packet to send it to 16.1 in VPN yellow, you better use label 42. So this guy is only going to use label 42, and that's the inner label. Remember I talked about inner label and outer label. That's the inner label that we are talking about, that this PE2 will use to send packet out that way, and this PE actually assigns it. So what is route distinguisher? And this is how you configure your VPN, okay, 3-4 commands. You give it a name, IPVRF, stands for Virtual Routing Forwarding Instance. That's what we call a routing table that is associated with each of the VPNs. You have 10 VPNs, you're going to have 10 VRFs on your router, and you're going to have a global routing table in addition to it. Global routing table only carries the core routing information, and this guy actually carries the VPN routing information. And that's how the two routing protocols, the two routing updates are kept separate. A route target is to say, hey, what am I going to import and export out of this particular routing table that is associated with this VPN? Okay, so we also limit that through these additional attributes right there. So that's pretty much the way you do it. And now when you look at layer 2 VPNs, the next couple applications coming up follow the same basic procedure. The core doesn't care for the services. Everything now on goes on is going to go on between PE1 and PE2 until we get to the QoS section and traffic engineering. Okay, because traffic engineering is very just particular to the MPLS VPN service provider and has nothing to do with the VPN sites. Your traffic engineering tunnels don't extend out to your subscribers' network. Okay, it's just a specifically core technology, MPLS core technology. So in the forwarding plane, we looked at the control plane. In the forwarding plane, packet comes in from, yellow VPN site. This guy says, okay, I've associated my physical interface to VRF yellow. So it looks at the yellow VRF routing table and it says, okay, I need to append a label, VPN label, appends a VPN label, looking at the IPv4 prefix. Then it tries to put the packet on the egress interface, and it, appends the second label, which is the IGP label, right? So all starting from yellow IPv4, all that's hidden. This guy only looks at the purple label right here, and it switches packet to this guy. This guy will take the purple label, swap it with a blue label. Remember, it swaps it with a different number, and it says, okay, I'm going to forward the packet onto this guy. Now, there's a mistake here because this yellow bar should have been here. And when this guy gets that packet, it looks at the yellow, field and says, oh, yellow field is out this particular interface. I know which routing table to look at, which VRF instance to look at because it's yellow VPN. It looks at that routing table and forwards the packet on to the VPN site, correct VPN site. Okay. Because this physical interface is also in its VRF instance as an egress interface and it's directly attached to the yellow VPN site, unless you by mistake attach it to the blue VPN site, only that time you're going to misroute the packets. Other than that, you know that, where you're forwarding your packets to. And again, it's forwarded as an IP packet. And that's how, when you look at the security aspect, do I feel secure enough? Do I, feel strong enough, or do I have faith in this technology to actually give my routes and my, critical company's traffic, email traffic, for example, to the service provider? We hired a third-party vendor called Mircom, and they use Cisco routers, and for all these applications, they thoroughly examined and evaluated and looked at the routing tables to make sure that the two VPNs that weren't supposed to be talking to each other weren't talking, that the labels coming in on an interface that, weren't supposed to be labeled were actually getting rid of, the interfaces actually were getting rid of those packets. This type of analysis was done by Mircom company. The white paper is available on CCO, so you're welcome to, download and look at it. But MPLS network, it inherits some of the security gaps from your IP technology, right? Because it's all based on IP technology. Another thing is human errors, right? During provisioning, people can make mistakes. So when you look at entire MPLS VPN network, the first concern is where, what device is exposed the most and who can attack and where can it be attacked is, of course, your provider edge devices, right? PE devices, because they're sitting at the edge. So the most concern is how do I secure that device? And some of these things that you're going to look at, some of the tools that we have are pretty much what you're used to of using. So my attack point is appearing PE. It could get attacked in the signaling plane, or a VPN site could just send me thousands of routes, right? Or BGP dampening might be having an issue in their network, and it might cause, the routing instability in my network or the provider's network. So those are the things that you need to look at. access list, privilege levels, all of that can be employed within the VPN to actually secure that VPN from the users of the VPNs. Okay, because the statistics says that 80 to 90% of the attacks come from the users within the same VPN. Next thing you can do is all the protocols that we are talking about supports MD5 authentication. So turn on MD5 authentication between the two peers. BGP dampening, filtering, you can limit the maximum numbers of prefix you're going to be accepting from the particular, customer or particular subscriber. So that you can do, per VRF, route limitations, etc. Class-based policing is another thing, is rate limit the traffic as it comes in, ingress to your network. So if this particular customer is buying only 10 meg and you see 20 meg, 30 meg and they're not supposed to burst, then do rate limiting on that interface for that VPN traffic. Firewall encapsulation, again, you can use that as well. There are three different encapsulation methods, three different encryption methods, because encryption is becoming more and more critical these days in the networks, right? So VRF-aware IPsec, all that means is the subscribers don't have to change anything. They make IPsec tunnel, configure IPsec tunnel. The only thing different is that they're going to be terminating that IPsec tunnels on the PE. Service provider says, okay, your IPsec tunnel one from VPN blue, I'm going to map it to VRF blue. So thereon the traffic is not encrypted, and we rely on the MPLS VPN technology to keep your traffic separate. If the customer or subscriber, you really need encryption end-to-end and everything must be encrypted, then what you can do is for some sites that requires encryption, go ahead and do overlay CE to CE. Just build your own CE to CE IPsec tunnels as you're used to normally. Doesn't change anything. Another thing, a solution we are coming out with pretty soon, it's in EFT right now, is CE to CE dynamic large-scale encryption, which is a VPN group-based encryption, so that you don't actually have to build the tunnels. Neither do the providers have to decrypt the traffic and build IPsec tunnels and map them to VRF on their end. It's completely independent of the service providers. So that's one less thing that you have to rely on the service provider, and the one less thing that the service provider has to worry. You can turn on IPsec encryption here and still use point-to-cloud connectivity and not have to fully mesh your site CPE to CPE where you need encryption, and just rely on your service provider to fully mesh your sites, and yet you have encryption, C to C encryption. Additional services, because I talked about traditional IP services in the managed shared services area, what do we have? DHCP, for example, NAT I mentioned already, address translation, very flexible, where you have to do address translation, because if the provider is providing services to the customers, that needs internet connectivity as well, right? You got internet traffic as well. So, this type of connectivity, and if they're using the private address space, of course, somebody's going to have to do the address translation, right? Service provider can add this service and say, hey, Mr. Subscriber, I will do address translation for you. Don't worry about it. Just tell me which sites needs internet connectivity, and when the time for that traffic or that site needs to access the global space, I will go ahead and deploy NAT wherever possible. Takes a load off the enterprise customers, because, hey, they don't have to worry about going out and buying a, public space, right? Or if they didn't have one already. So, other thing we are looking at is redundancy, HSRP, VRRP, GLBP, they're all made VRF aware, VPN aware, so they've been virtualized. Cisco iOS firewalls been virtualized, the security area. And multicast VPNs adds a great value, and a lot of customers are actually, especially in the financial world, have multicast applications. So I mentioned connectionless MPLS VPN network, point-to-cloud connectivity. Customers don't have to worry about fully mashing the sites. Providers will do it for them. All these things we will also want to benefit, for multicast service. So we came up with multicast VPNs. For the unicast traffic, what did we have? We had VRF, virtual routing forwarding instance. Well, we built the same thing, multicast VRF using multicast routing protocols. So now, in addition to the basic connectivity VRF, you're also going to have multicast VRF. Service provider only needs to enable native multicast in the core. Subscribers, Red VPN got a server sitting there. Red VPN maybe it's got a client sitting out here, the receiver sitting out here. Doesn't have to worry about fully mashing for multicast traffic from here to there. Okay. All it needs to do is connect to the service provider and it will take care of it. Multicast packet replication, even the source sends it out, the PE will do the multicast packet replication. So you can get multicast VPNs from the service providers who support it in addition to the basic connectivity. Okay, so we looked at layer 3 VPNs, we looked at the architecture, we looked at a lot of the protocols, details, etc. We know what's going on. How do I utilize and what type of services do I build, right, for in this MPLS network? So layer 3 VPN networks, this is a service provider, these are the subscribers. Service providers can provide managed service, service provider can provide unmanaged service. Managed service is where service provider is going to come out on your CPE and control your routing, QoS, security policies, everything. So the subscriber totally hands their CPE to the service provider. Some service providers also sell the boxes as well. Okay, and they can provide intranet, extranet, all these different type of services. Those are for the subscribers wanting to get MPLS VPN services from the providers. Now, enterprise customers also want to subscribe, but they also want to have some, 2-3 segmentation in their network. So we're looking at an enterprise campus here that's doing VRF using multi-VRF. So it's a multi-VRF is a label-free, MPBGP free solution. All you do is associate whatever the routing protocol you're using in your network, whatever the routing protocol subscribers using in their network, and associate that routing protocol instance to a VRF. And it creates separate routing tables for different VRFs. And here we have red, green, and blue. That's what we have. Red, green, and blue, all these users belong. These users are part of red VPN. These users are part of green VPN. We carry that segmentation. We create two sub-interfaces. One sub-interface is going to pass green VPN traffic, another sub-interface is going to pass red VPN traffic. Same thing here. One sub-interface is going to pass green VPN traffic, another sub-interface is going to pass blue VPN traffic. And we got, again, the routing instance, right, EIGRP instance for red VPN, EIGRP instance for blue VPN, EIGRP instance for green VPN. All right, so now in our campus end-to-end, we got segmentation. I want to span that segmentation across my wide area network, but I don't want to maintain my wide area network. It's much cheaper for me to go to service provider and get a service. So what I'm going to do is I'm going to buy 3 VPNs for my service providers, give the service provider 3 sub-interfaces. 3 sub-interfaces is carrying 3 different VPN traffics. I got 3 different remote sites belonging to 3 different VPNs, and that service providers will actually help me extend those VPNs, and each site will get only its own traffic that the VPN that it's belonged to. This type of thing you can do, okay? So subscriber, MPLS, VPN subscriber doing full MPLS, the subscriber of the services only using the segmented routing tables. Then the enterprise customers, large enterprise customers, they have, requirement for having 5, 10, 20 VPNs. They have a large network. You might want to add more VPNs in the future. You might want to remove VPNs in the future. You have a pretty dynamic environment. You're rich enough, and you need the full control for end-to-end network. You own all the, infrastructure already. You can turn on this service and own your own VPN. So each VLANs you can map to each of the VRFs, red, blue, green, whatever, and map those segmentation onto the PE routers, and then take it to the other side and give, campus to campus, or this even could be your own enterprise-owned wide area network. But again, that's how you create segmentation and carry segmentation across the campus or across your own wide area network. And we are seeing few enterprise customers wanting to do this because they said, we'll pay a little bit more, that's fine. We'll buy more, GSRs and 7600s if we need to, but the critical thing is that we want to maintain the full control over how things are done, for our traffic. And some, hybrid model, it makes sense. I can get cheaper services from a service provider in one region, but I have data centers around the world, and I have, WAN connectivity, and I just want to maybe use Ethernet over MPLS and connect up my data centers, but I'll be in charge of that. Okay, so that's a hybrid model that you're looking at. So talking about layer 2 VPNs, let's quickly look at slide 59, where we're actually talking about any transport over MPLS architecture. Again, forget about these core routers because they don't play the role. Remember in PE, the layer 3 VPN, what did we use? We used MPBGP to carry the layer 3 VPN information. In the very beginning of the session, I mentioned what? Directed LDP sessions, right? So for layer 2 VPNs, point-to-point layer 2 VPNs, we are going to be using directed LDP sessions. So we have attachment circuit, consider ATM, coming from this VPN A customer. ATM island out here, ATM island out here. All they need is a transport over the wide area network. This guy is sitting in San Jose. This guy is sitting in New York. You go to MPLS layer 2 VPN service provider and say, hey, provide me a pseudo wire, provide me a circuit so I can connect my two islands. And to VPNA and VPNA site 2 right here, those islands, these pseudo wires are just like a virtual or like a point-to-point circuit. They don't think or understand or know or need to know that, labels are being switched and all these other things, and directed LDP sessions are turned on out here. No. Only PEs will have directed LDP sessions turned on. They will, again, for this site, VPI, VCI, this guy will calculate the label, tell it what label to use, label value to use if this guy wants to forward ATM cell out to that guy. So let's take a look at a frame relay over ATM example. What do we have here? The two frame relay sites. What do we get in with frame relay is DELCs, right? Is one way to connecting the remote site, customer sites to the provider's network. We have DELC 101, DELC 102, DELC 201, DELC 202. DELC 101, that's one DELC that needs to connect to 201. Okay, that's what we need to do. So what does provider do? Provider tells PE1 that, hey, create a directed LDP session with PE2 because I need to support this attachment circuit right there. And that's exactly is this configuration right here. This 11111 MPLS, route to this guy is the address of this PE1, and this 22222 is the PE address of the PE2. Those addresses, it already has the connectivity because our core is already working. VCID, we need a common VCID to create a common pseudo wire between the two. And then we calculate the label for that particular DELC 101. This guy says for VPN, label 10. Okay, fine. This guy says use label 10 actually to send anything to 201. This guy says fine. And so this guy has already gotten this label 10 from this PE2, right? Frame comes in, it looks at 101, puts label 10 on. The interface, core facing interface puts the outer label. Outer label is exchanged with this guy. This guy sends it to the last guy in the path, removes this LDP label. This guy looks at the label 10. It says, label 10 means DELC 201, and forwards the packet out over that particular interface. Okay? And you can do this over and over again for a lot of the applications, layer 2, layer 3. And this is just an example of service provider providing connectivity service between the ATM islands. In the metro Ethernet area is another, opened up another opportunity too for these service providers is, a lot of the data centers connectivity or the subscribers need to extend their data center's reachability. They can do Ethernet over MPLS. From here to here, port-based or VLAN-based Ethernet over MPLS, just provide a pseudo wire. So again, point-to-point, looks like a point-to-point circuit. That's all it is. It's a tunnel. And the traffic is forwarded, Ethernet frames are forwarded to the remote data centers. That would be like one of the applications. Same thing happens when we look at the layer 3 multi-point connectivity, okay? I just switched from layer 2 point-to-point connectivity to layer 3 multi-point connectivity. Layer 3 multi-point connectivity is called Virtual Private LAN Services, VPLS, supports Ethernet or VLANs type of domains. And what we do here, pretty much the same thing. But because it's a multi-point connectivity, we got to have a fully meshed directed LDP sessions with all the PEs where the remote VPN sites needs to be attached to, right? So instead of point-to-point directed LDP sessions just between the two PEs, directed LDP sessions will be fully meshed between all these PEs. Now in Ethernet domain, what do we have? Instead of IP addresses, we have MAC addresses, right? So with MAC addresses, again, what do? We map label with the MAC address. That's what we do, because that's what we got. Our FAC is forwarding equivalence class here is a MAC address. How do we do the MAC address learning if this is a VLAN interface here or this is a port base? We need to do VLAN learning. We got a virtual bridge and switching instances are sitting inside this PE1 box. Remember in the layer 2 point-to-point, our attachment circuit directly mapped to the pseudo wire. Here, that is not the case. It needs to consult additional virtual table where it has the label mappings for the MAC addresses. So let's take an example for this one here. How does the switch here and the bridge learn the MAC addresses? Packet comes in with a source MAC address 1. It says, need to send it to MAC 2. This guy here will multicast the request out to PE2, PE3, PE4, however many P's are sitting out here, because it doesn't know where MAC address 2 is sitting. Okay, so it needs to do the learning first, right? So it's going to do the learning, MAC address learning. It learns, this guy says, hey, responds and says, hey, MAC address 2 is I know where it is. And if you want to send any packets, MAC address 2 as a destination, use label 201. And we again build pseudo wires. In this case, we'll have like fully matched pseudo wires. And the way we forward the packet is it builds actually a table called VSI, or Virtual Service Instance, or Virtual Forwarding Instance, VFI. Okay, and what it's got is the MAC addresses, mappings with the labels, and the interface that it needs to put the packet out to. And that's how basically the MPLS Ethernet multi-point service technology works. And a lot of the service providers are now beginning to offer this. This is, in fact, a couple of years ago, there was a huge hype about this solution because customers thought, hey, great idea. We can extend our VLANs, right, without having to worry about like spanning tree protocols and all these broadcasts across our networks. We can take this campus, get service from the service provider, get a transport, attached to that campus, and have a broadcast-based domains and just work with Ethernet. It turned out that the scalability is still an issue because these guys, as the MAC address learning, it still has to multicast, right? And it has to replicate the packets. So the signaling and replicating the packets, that's still pretty intensive. So it's gaining a momentum. It's just growing up. It's in that phase right now. And if you had a larger networks that you needed to support, because MAC address limitation is like about 4,000, you use a hierarchical VPLS. UPE faces the customer network, NPE faces the provider network, and you take these guys, you take a whole bunch of VLANs like VLAN 10, 20, 30, 40, and you multiplex into VLAN 100, for example, only one VLAN. So you might have hundreds of VLAN, enveloped into one VLAN. So as far as NP is concerned, it's only seeing one VLAN, building the pseudo wires. Same thing, directed LDP sessions goes out in the clouds. Your pseudo wires are in the clouds as well. And again, that's how we provide the connectivity between two end-to-end devices. So hierarchical model, in any case, anywhere where the scalability is the limitation, you basically look at the hierarchical model. Just a pictorial view of, I got 3 different customers with 3 different VPLS segments. I got directed LDP sessions fully meshed, but hey, I only have a blue and a red VSI here. This guy doesn't carry green VSI, doesn't carry green table because doesn't have to support that particular VPN customer. Okay, so again, things are made scalable because the PEs won't carry all this additional extra information unless those VPN sites are directly attached to them. And that applies to all the VPN technologies, layer 3, layer 2, point-to-point or multi-point connectivity. All right, so you can just look at pseudo wire for this guy out here, red VPN, will talk to this guy and it will also talk to this guy, and it got multiple paths as well. If it needs to talk to this guy out here, it will go over the top path. If it needs to talk to these guys out here, it will go through the bottom PE. I will use a couple minutes to explain QoS because QoS is used to guarantee the bandwidth your traffic needs and to deal with congestion problems, right? And all the tools, those are used in IP QoS networks or IP networks to do the QoS service to provide the service level agreements. All those tools, queuing, dropping, low latency queuing, everything supported in the MPLS network. The only thing changes, as I mentioned earlier, is instead of looking at type of service field for IP packet, we look at experimental field to do our classification and to do our markings, etc. So what happens for a subscriber? And how does MPLS service provider provide service classes? Most of the service providers provide like 3 to 4 service classes, like platinum class, gold class, silver class, bronze class, right? And then charge differently and, support different amount of bandwidth guarantees in each one of the class for these VPN customers. So if you look at the end-to-end network, this is enterprise network here that also has deployed QoS. Now, enterprise customers sometimes have 5 classes, 10 classes, 15 classes. What happens when they go to the when they go to their service provider that has only 3 classes or 5 classes? Well, you're going to have to reconstruct the policies for right at the edge right here. Okay, and match whatever the numbers of classes your service provider is providing you with. So you got to multiplex and think about how am I going to multiplex these 10, 15 classes I have to the 5 or 4 classes that my service provider provides. So ask your service providers, what markings are you using, how many classes are you giving, etc., and make sure those are the markings you use right here. If not, a lot of the service providers, what they do, if they are not managing this CPE, they don't trust the markings, those coming from the subscriber. So they're going to remark the traffic on that PE1. And let me go to this slide right here, 72. Because if they're going to remark your packets, right, if the service provider is going to remark the packets coming in from the subscribers, they're worried. How is my traffic handled QoS-wise? What kind of treatment my traffic is getting for each one of my classes throughout the core, right? 3 different modes that your service providers can use to deploy the quality of service. And when we talk about the modes and 3 different modes, all it means, okay, once you understand one mode, then you'll understand the other 2. It's no big deal. Is at the egress, traffic comes in. Of course, they remark the traffic depending on whatever the values they're using and numbers of classes they're using. Traffic came in with DSCP3, automatically copied to MPLS experimental value 3. Service provider changed the markings to 2. Traffic was treated based on experimental bit 2 or value 2 or priority 2 throughout the core. When the traffic comes to the edge, that's when the whole thing, this whole mess about do I have the right markings come into play. Because what markings the service provider propagates to the subscriber network for that traffic from their network as the traffic goes from PE to CE. Uniform mode says I copy whatever they give me, but I change the values later on. I, do the treatment on the traffic based on my selected changed value. When the traffic comes here on that egress interface, I still do, what I do is I take the experimental bit values and I copy it into the DSCP field. I do the treatment on the egress value based on the DSCP2, and that's the packet that the customer is going to get. Guess what? That could be very confusing for the subscribers because now they're getting the traffic with marked value of DSCP value 2 when they were expecting this traffic to be DSCP value 3. Because what that means with different values is that they have allocated different resources, right? DSCP3 might be getting 2 meg bandwidth and low latency queue service in their network, whereas DSCP2 value may be getting, bandwidth if it's available. And it might be just really, low priority type of class in their network. So that really creates a problem. So that's why subscribers really need to be aware of how my service provider is marking and what are they handing me off. Okay, and this is something that the providers also can talk to their customers as to how and what they're doing and handling their traffic QoS-wise. So that's the key thing that I wanted to mention. And then the other two modes, different things happen at the edge, different values are propagated. You guys can use these two slides as your reference. But just be aware what's coming in to my network. Is it coming in with the same markings or is it coming in with the different markings? Traffic engineering, I mentioned this earlier, is we use it for congestion control, constraint-based routing, because, we want to engineer the paths the way we want to, right? We want to have that freedom. We don't want to rely on the best path that my IGP has calculated. If OSPF has given me the best path, maybe it's given you the best path based on the fewer numbers of hops that it needs to cross, or maybe on the, least cost path. But what happens if all the traffic just gets puts on that least cost or, shortest path? You could end up congesting that, and then you got all these other paths in the network, those are just sitting empty, right? You want to have complete knowledge of what resources are available in which part of your network so that you can do better capacity planning in your network. What happens if my node fails, link goes down? I have, a lot of important traffic coming from my customers. I want to be able to quickly converge so that, find a backup path as quick as possible, like in the milliseconds, so that I minimize my packet drop. Okay, so those are the things why I want to use traffic engineering. And if you go on slide number 81, right after the fish slide, and even though I'm skipping the slide, I guarantee you I am not skipping the material that you need to know, okay? So the stuff that I have, you're not missing out on the slides that I'm skipping, just know that. Use that material more for reference. I'm covering it right here. So I have two paths available right here, right? If I want to go from router A to router F or router A to router G. What happens? I have OC3 right here and DS3 right here. This is without traffic engineering, okay? This router sees the aggregated traffic and says, okay, 80 meg. The only knowledge it has, its own link, and says OC3, it can handle. I'm going to send all the traffic this way. 35 meg traffic is dropped right here because DS3 cannot handle the entire 80 meg traffic. If you switch it over, engineer your tunnel and say, okay, maybe tweak your IGP attributes, get your traffic going this way, it's the same thing. Right here, DS3 is going to drop the packets. We want to minimize that. So what we do is we look at the head end right here, and we say, I'm going to build tunnels. And I'm going to say, because I know the traffic, I have a limitation somewhere in the path, in the network, that's going to drop a large amount of traffic. And, it's going to take me, several weeks or months to upgrade this DS3 right here, right? Or I don't have budget to upgrade this DS3. How do I intelligently, engineer my network so that I don't drop a lot of traffic right there? You create a tunnel up here, and you create a tunnel down here. So 40 meg traffic destined to this router goes over the top tunnel, 40 meg goes over the bottom tunnel destined to router G, and, we've efficiently engineered our traffic in the networks so to minimize the packet drop. So how do we do this? Right, traffic engineering tunnels. Where do I build it? Depends. You can do it PE to PE. You can do it one hop. You can fully match it between your 50 PEs that you have. You got a lot of flexibility. But when you look at it, you have a head end in the tunnel. You're going to have a head end, and you're going to have a tail end, and you're going to have midpoints. The head end is the one that relies on the IGP. And this is why I said earlier that you want to use traffic engineering application. You got to use OSPF or ISIS because they are link state based protocols. Okay, that's why you need to use OSPF for ISIS. You don't want to do traffic engineering, use EIGRP, static routes, just fine. But the head end, in order to build those type of paths, we need to have, the head end needs to have a knowledge of every bandwidth, every link, resources available in the network. Next thing it needs to do is it needs to calculate the paths, right? So head end uses something called, a procedure called CSPF, Constraint Based Shortest Path First protocol, and it calculates the paths. So head end takes all that information coming from IGP. IGP goes around and says, I know where's what, how much bandwidth is available, go ahead and figure things out. So head end takes all that information. Once that information is taken, it does the path calculation. Once the path calculation are done, now it needs to say, okay, I need to consult my tail end and meet points and say, hey, I'm coming up with this best path. Can you all guys handle that? Okay, so that's where these path setup, trunk admission control, all these step 3, 4, 5, 6 come into play. And I think this is the information I added on, so some of you might not have it in your slides. But in any case, what happens is moving on to slide 85 that says path setup, trunk control, or you got this RSVP and TE tail end head end, and the arrows with path and RESV messages. We use RSVP, RESV or reservation messages from the TE head end after it's done calculating with its CSPF stuff, and it sends the path messages from head end to tail end. And the tail end then will say, okay, yeah, go ahead, and it requests the bandwidth information and it requests the labels. So tail end says, yeah, for all this stuff that relies here, we can build a tunnel, but use these labels. So RSVP then will take these labels and the bandwidth information in its reservation messages. Path messages are request messages. Reservation messages are reply messages. So the bandwidth information and all this for every node comes back to the TE head end and says, hey, TE head end, you said 20 meg tunnel. Can we build it over these paths? Yes, we can build it. Every point will reserve a bandwidth pool. From the general bandwidth pool, it will reserve 20 meg for this tunnel, and it will say use these labels. Every hop to say use these labels if you want to forward the packets over these tunnels destined to this tail end. Okay, that's how all the control plane gets set up, right? So that's part of control plane of your traffic engineering. Just because you set up tunnels doesn't mean that the traffic is going to be forwarded onto those tunnels. Okay, you got to take additional step to say, how do I want to route and which traffic do I want to route to this tunnel? You can do it statically, doing static routes, IP route, whatever, subnet to tunnel 0, tunnel 1. You can do auto route. It will automatically select the tunnels. You have multiple tunnels, and you want specific traffic to go over specific tunnels. You better, rely on some other methods. You can also use policy route along with traffic engineering tunnels as well. Okay, so those are the methods you can use to say, I got the tunnels, I got the bandwidth, I know we can handle this much. Let's put this traffic using this method over these particular tunnels. You don't want to go through any of these headaches. You can look at Tunnel Builder Pro, and it helps you figure out everything. Don't have to worry about a lot of the configuration and stuff. But there are so many knobs in traffic engineering that you can really specify and have, unique qualities for each of the traffic engineering tunnels. You can prioritize them. Less priority traffic engineering tunnels, when the priority traffic engineering tunnels comes up, you can tear it down. And when the priority traffic engineering tunnels doesn't need that much bandwidth, you can bring the backup tunnel back up. There are a lot of things you can do with traffic engineering. Yes? Right, good question. So if you reserve, let's say, even for, say, priority tunnel, and you reserve 15 or 20 meg of traffic, and it's just sitting there, and what my other traffic needs to use this bandwidth, will it just sit there and not utilize? No, it will get utilized. Okay, so that bandwidth, if 40 meg traffic, if it's only 40 meg link and 20 meg is reserved for your tunnel, that tunnel doesn't have any traffic. That 20 meg is available to other traffic. But as soon as more traffic becomes available over that tunnel, the bandwidth pool, there's a common TE bandwidth manager, and it manages your bandwidth pool. Within the bandwidth pool, you can have one big bandwidth pool, Or for DSTE, you can have subpools as well. And it manages it quite well. Very similar to QoS. You have multiple classes. You reserve for your low latency queue, you reserve 1 meg. For another class, you reserve 512. Another class, you reserve, 56K. And what if I don't have any voice traffic in low latency queuing? That bandwidth does become available for the other traffic, okay? So your bandwidth never just sits there. If the traffic is not available for that particular class or for that particular tunnel, then we make it available for other traffic, okay? Good question. Next thing we talked about is the protection mechanism, if link goes down. So let's take a look at, I have a primary tunnel I built from A to B to D to E. Link fails. This is link protection slide 87. A to B to D to E, that link goes down. Okay, what happens? We build a backup path or B to C to D. That's the point we've selected, that if this link goes down, I want to quickly route stuff over there. So what we do is this router B learns the label from router D, right? Router D says, hey, you want to send the traffic this way for, out here, use label 14, for example, right? Because this is what we've been doing, right? The neighbor tells the other guy, use label. So this guy says, okay, I'm going to use label 14 if I'm going to send you the traffic this way. Backup tunnel says, use label 24 if you want to send the traffic this way, okay? This link goes down. What we do is we take this primary tunnel and we encapsulate it into this backup tunnel that we have. Why do we do that? Because we don't want router D or router E to know that the link has gone down here and make everyone go crazy and try and recalculate the paths, etc. And then we have to wait until everything converges and, packet drops and the convergence times might go through the roof. So routing protocols takes several seconds, minutes to converge. In this case, we can get like 30, 50 milliseconds type of convergence time. So what this guy does is, this guy says use 24. So if this link goes down, what we're going to use? We're going to use both labels. We're going to use label 14 that this guy expects and label 24 that this guy expects. Except for label 24 will be outer label because that's who we are sending the traffic to because this link is down, right? So this guy says 24, I get a packet with 24, that's fine, that's a valid packet. It knows to send that this guy is the last guy or a tail end, removes 24, hence the packet over here. This guy sees the next packet, which one is it? It's 14. It's the one it's expecting to see from this guy, right? And that's how we build the path. So this guy is going to say, okay, good label, I'm going to forward the packet as if nothing's happened, as if this link here has not gone down. And so that's why we build the backup paths, we keep the backup paths in the table. So this link goes down, all it needs to know, the time it takes for it to realize is the interface down. As soon as it senses the interface down, this path is ready to start routing the packets over that way. Yes? One way, okay. Inherent, great question. Are these, do we need to do both ways, build two tunnels for traffic there to here and here to there, or single tunnel? You need to build two tunnels. MPLS inherently is a unidirectional thing. LSP paths are built, remember the first slide that we went through? It was built in one direction. If I had to show you the other direction, I would have had to walk through this way to say which labels are allocated again. Okay, so at the very basic, it's a unidirectional thing. So you want to build a traffic engineering tunnel going from here to there, that's a one tunnel. You want to provide the same treatment for the traffic going from here to there, you got to build a second tunnel.
In this case, the router will have to know that this thing has gone down or the path is going back.
Yeah, the router will only know that the link has gone down. It doesn't have to mess with the routing protocol, the routing table, and says the route gone down. Let's remove the route, let's relearn the route, new route, let's reallocate new labels, stuff like that. All those steps we skip, okay? In the node protection, what are we protecting is the node. If the node goes down, for example, instead of a link going down, what we do is instead of building the tunnel and the labels for the next hop, we go to next hop. And I'm not going to walk through that. You guys get an idea of what the protection is all about. Path protection is a lot more work. Hardly anybody deploys it. You can get a lot out of link protection and node protection because of the work you have to put in and the sort of the return on investment for what you're putting in and the convergence times that you're getting out from the whole solution. So T deployment scenario, I have a congestion point in the network, and I have two paths, right? This is the shortest path. Everything is going over this way. I want to take this bulk of traffic, and I want to engineer a traffic engineering tunnel and reroute it in other direction. So what happens is, eventually, if this link here is oversubscribed, we want to lighten the overhead. We want to lighten the traffic load on this particular path. We build a tunnel right here. Say all the internet traffic go over tunnel 0. So at least we take that load off, and now this oversubscribed links, as the more bandwidth becomes available for other type of traffic. If you want fully meshed from every PE to every PE because you have a strict requirement from all VPN side, or you may have your other, POPs, point of service provider, point of presence out here, you're doing voice trunking between every sites and you really need that amount of bandwidth guaranteed, then you can fully mesh your tunnels among all the PEs that you have. And the third scenario is, again, the fast readout application that we talked about. I have a primary path going on the top, all the red arrows. I have a backup path. I'm going to use this router. This is my backup path. If this link fails, this is my backup path. If that link fails, and this is my backup path. If backup path right here, I can go this way if this link fails. So these are you have to identify, where the points where you want to build the tunnels and which points you want to build your backup tunnels around. Okay, so that is the whole story about the traffic engineering. You can do class-based traffic engineering tunnel and provide a virtual lease line type of service because your voice traffic marked all experimental bit 5. All the experimental bit 5 value traffic go over tunnel 0. And, all the traffic marked with maybe experimental bit value 4 go over this path. These type of things you can do. Even based on the QoS, you can, route your traffic over the traffic engineering tunnels. And this is a sample configs you can look at. Next thing is high availability. I'm going to cover this very quickly too because, you can build redundant paths, have redundant devices, right? 2 CEs going to 1 PE type of thing. But if you have a key PE or P devices that has dual route processors, okay, that's if a route processor fails. How do we quickly go over to the new route processor? Because when it switches to the route processor, unless you have HA or high availability deployed, it's going to want to recalculate everything. And the times could shoot through the roof, okay? And that's what we want to avoid. So what we do is, with the dual processor, all the protocols that we have, LDP, MPBGP, RSVP, we make it graceful restart capable. Okay, so that's what your routing protocols need to have. As well as the processors that we use, that device that has dual processor needs to be able to have stateful switchover capability. So in the IP LAN, we also have NSF, SSO, non-stop forwarding stateful switchover capability. In IP role, right on top of that, we have MPLS HA capabilities built into very similarly into the protocols we use for MPLS. That's how simple it is. So that primary route processor fails, all the information is copied and checked periodically, updated to the backup route processor. So control plane goes down. Of course, LDP, all these guys are TCP based, right? So you still have these sessions, the sessions go down. Forwarding path responds to your control plane. Control plane goes down, the forwarding plane wants to stop forwarding. That's what we want to eliminate. If the control plane goes down, we want to say, hey, forwarding path, that's fine. Use the original old information. And that's where we mark stale. All the routing, all the information that we have, all the bindings that we have, labels to prefixes, we mark it stale, and we tell with the graceful restart capability of this protocol to keep using the original information until the new routes and the new labels are calculated. Okay? Once the new routes and new labels are calculated, we check, is the old information same as the new one? Fine, then we just refresh it. Is it different? Then we go ahead and incrementally update whatever that is different. The backup processor now is an active primary processor, and your original primary processor sits as a backup processor, gets all the information periodically updated, and it gets ready just in case your primary processor fails. So that's a whole story of high availability. The story of management is you build a network, right? It's not a, live happily ever after story, right? You got to go back and check and see, what do I need to improve, right? Anything that needs to be improved, you check that and you change your parameters, you change your attributes, you change your values, etc. And that's what we have is embedded management. We have all these MPLS-based tools, CLI-based tools that you can use in the, your MPLS devices. We have ISC, and we have Internet Service Center is a provisioning tool, etc. We have an MPLS diagnostic tool that will actually help you troubleshoot and verify your MPLS networks. So that's what we have like in the management. There are a lot more tools you can look up on the CCO, but that's just an example of what we got to help you also verify, troubleshoot, and improve, fine-tune your MPLS network. So I really appreciate you guys staying here a little longer. Thank you very much for coming, and I hope you guys all learned something. Thank you.